I would like to begin with a reminder for everyone that next Tuesday is our exam number 3. Right? So it's not a Thursday the way the previous 2 exams were. It's a Tuesday. Make sure you don't blow it. Especially don't blow it by coming late. All right? A couple other things I want to review with you. First of all, Clicky Data is updated as far as last Thursday. All right, so that's lecture 24. And in terms of how many questions possible, section 1 had 53 questions possible, 16 lectures. And you guys, section 2, you have 51 questions on the books in 17 lectures. So the 2 sections are a little bit apart. The 85% mark, and it is different for each as a result. And this is the mark which, if you hit 85% participation, whether right or wrong, you get 25 out of 25 on your semester grade. Right? So if I were doing semester grades today, here's what it would be for section 1. And here it is for you guys, section 2. If you have 44 questions answered, so you go to L5, answered. L6 answers. L7 answers. And all the way out to L24 answers. And in your case, it's L24.2 because section 1 didn't have anything last Thursday. You guys had 1 question. You add up all those answers, and if you have 44 or more, you have 25 out of 25. So that's where you want to be. Now, if you think about it, 51 minus 44 is 7 questions. So if you've missed 7 questions this semester out of 51, you're still good. You're still going to get 25 out of 25. Now, at the rate that we ask questions, 51 questions in 17 lectures, that's an average of exactly 3 questions per lecture. Now, sometimes we have more than that. Sometimes we have fewer. Like Friday or Thursday last week, we only had 1. But on average, it's 3. And so you've got basically 2 lectures to burn, and you're still going to come out okay. But hopefully you haven't done that. Hopefully everybody's up at 100% participation. All right. But if you've missed 2, total of 6 or total of 7, you're still good. Otherwise, you have to figure out your percentage and then your points. Now, I want you to jot down this proportion here, if you will, so that we can go over it together. And I have some clicker questions related to this proportion. So get your clicker out. Get your calculator out, too. If you don't have a calculator, you can use your cell phone. If you don't have a cell phone, God bless you. You're going to have to use pencil and paper. But even that's not too bodacious. Push this thing as far forward as I can go. Yeah, Deborah. Deborah has a question about special study groups, and the answer to that is yes, we're going to be doing that this week. And they'll be running over the weekend. You'll have your actual special studies group session, if you sign up for one, over the weekend. You know, Friday, Saturday, Sunday, Monday. And then exam on Tuesday. Question? What? Deborah? Students, let me have your attention. A student, one of your comrades, just asked me, do we have class on Thursday? Because there's a big football game and campus closes down for classes at 3 p.m. So we're going to have class. What? I never said the other day we're going to cancel class. Don't try to trick me. No, we'll have normal class on Thursday. Last time campus closed down at 12, so we did have to cancel. This time it's 3 o'clock, so we're good. All right? Nice try, though. All right, so here's your proportion. You have to figure out your percentage first. So for you guys, how many out of 51? Now, I'm going to give you an example here in a second, but you figure that out, you solve this proportion, and then the last thing you have to do is you round up. So if you come up with 22.1 points for your points, then I always round that up to 23, or from 22 to 23. You know, so if you have 21.001, I'll round that up to 22. Okay, so always round up your answer, and you're going to have to calculate that in just a minute. So let's start with some clicking questions. And when you turn on your machine, make sure it's on frequency BB. Okay. All right. Dare, you want to verify? Okay. Okay. All right. Now you want to click before I start my countdown. If you're still fussing before I start my countdown, the last 10 seconds, there's a good chance I'm going to click it closed before you click in your answer. All right, so don't let me catch you napping. All right, question number 1. John Q. student in our section. He's answered 38 out of a total 51 questions as of November 12th. What is his participation percentage? All right, now the correct answer is on there. You go ahead and calculate. And this is the first thing that you have to do. If you're below 85%, this is what you've got to calculate. Yeah?
Are the clicking points going to be on the clicker participation or on like test?
The bonus points? Yeah, those are bonus points. They're separate. They're out there. Don't worry about them. They're on the books. They're not going nowhere. Okay. Did you get some? Good. What? Oh, sorry. I thought I opened it. Matt, you got it now? All right, go ahead and put in your answer. And hey, you guys, if you're below 85% on your clicking percentage, this is the first thing that you've got to do. Figure out actually, everybody should do this to figure out if you are 85% or higher. If you're 85%, this is all you got to do. If you're below 85%, this is the first thing you got to do out of two things. Okay, 30 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys got. Yeah, most of you got that. Uh-oh. Yeah, 85%. Some of you voted for 85%. And some voted 25 out of 25. No, this guy's below 85%. It's actually 74.5 approximately. All right, now let's do another question. Here's your actual calculation. Hopefully that's easy to do. Most of you got it right. Okay, hit the refresh key. And let's do a calculation. All right, and you always got to hit the refresh key when you're about to do a calculation. And your calculation is how many points out of 25 does he get? Now to do this, you got to solve this proportion. So take your time, do it with a neighbor if you're a little bit nervous. And Leah, just figure out, how many points John Q. student has, and you're good. And then type that. And don't forget to round up. And if you guys want to come to office hours tomorrow and double check your grades, you know, as of, you know, this past weekend, I could sure do that for you in office hours. I do it a lot this time of the semester. Everybody's always nervous about their grade and stuff. So if you can make it to office hours, fine. If you can't, just text me or message me in web courses. Always ready to help. Matt? Yeah, put in the number out of 25. Yeah, so if your answer comes up 14, type in 14. Now, most of you guys are going to have 25 out of 25. But if you have a friend that is a little bit below 85%, now you can help them out. If you get it right. Thirty seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Key woo, let's see what we got here. You ready? Good. 3 minutes. Anybody vote for this? 22? Raise your hand if you voted for 22. Sweet. Actually, I can... Oh, man, you did better than the morning class. 86%. Nice. Two people voted 21.9. No. You forgot to round up. All right? Now, as I mentioned, I want you to be able to do this with a friend if they have a question. Or in discussions, you know, although it's not really kosher to share your grade information in discussions because it's a violate. But if you're doing it, I don't know if it violates your privacy if you do it. But I'm not supposed to do that in discussions. So, are you clicking? Good. I don't know. Somebody else was having the same complaint. I don't know where he's sitting, but anyway. All right. Let's talk about the electromagnetic interaction, or as in a lot of physics circles, theoretical astrophysics like relativity and stuff, the Coulomb interaction. Now, this little baby got into the laundry basket, and this little baby's mamasaurus forgot to put in one of those little dryer sheet things, cling free. Okay? So this little baby's got static cling going on there. And static cling, or static electricity, is a little bit of static electricity out there, it sounds like. By the way, you know what? I went on my camp out this weekend, and it was a nice camp out, but I didn't have any disasters. I didn't get rained on. I didn't get bit up by mosquitoes. I didn't even get chased by a bear. But we had a nice camp out. We saw the stars. It was beautiful stargazing. It's great. Electrons. Electron. Greek word for amber is electron. I've got it spelled out in Greek letters and also the transliterated Roman alphabet. The idea of static cling, rubbing something together, Pamela, and getting some electric charge built up. Don't look at Jessica. I'm talking good. It's called triboelectricity, and it comes from the Latin word tribulum, which is their word in Latin for a threshing sledge. Now, what we have today are big international harvester threshing machines, big combines. But in the olden days, they had to separate grain, wheat, from the chaff. You had to use something called a threshing sledge, and basically kind of pounded on it and thrashed on it and separated the grains of wheat, the grains of corn and so forth from the stalks and the chaff. The word tribulation comes from the same thing, from the same root word. And it's something that we've observed, since the earliest times. Because this stuff called amber. Amber is kind of it's not really I guess maybe you could call it a stone. It's a fossilized piece of pitch from a pine tree. And I guess if you get the right kind, it looks beautiful. And so it's a precious fossil, precious stone. And people notice that if you rub it, it'll pick up little threads and, stuff like, little pieces of paper and stuff. Although back in the olden days, they didn't have a whole lot of paper. Matter of fact, they only had papyrus. So I guess you could pick up little scraps of papyrus with it. Now this diagram here shows triboelectricity, frictional rubbing of two different substances, human hair and a plastic comb. Now the plastic comb acquires a negative charge. The hair loses some electrons, and so it nets a positive charge. Okay, now we were going to try to have the big Van de Graaff generator, the one that makes your hair fly out into the space, but we couldn't get it for today, so hopefully Thursday we'll do that. But anyways, this is an example, very common example. Here's a table. You can jot down a few of these, and just jot down the main term, triboelectric series. These are the substances which, if you rub them together, will produce a little bit of static electricity. And the one at the top, human hands, rabbit fur, glass, if you rub those together with something toward the bottom, like styrofoam or rubber or amber, then the amber will get some negative charge, and the human hands, rabbit fur, or glass will get some positive charge. All right? And so the charges separate by friction. And one of them likes to draw the electrons out of the other, and so therefore the other is stranded with missing electrons and a net positive charge. That's the stuff towards the top. Now right here in the middle is steel. It's considered neutral in the triboelectric series. Now there's no numerical rating system that I know of for triboelectricity, so they just kind of have a relative ranking. It's not like something that we design machines around, but it is interesting to know. And Benjamin Franklin is the one that first made a hard decision based on this triboelectric effect. He said, he figured out that there was two different kinds of charges. So he said, all right, let's consider the stuff on the glass rod to be positive, the stuff on the rubber rod to be negative, and those positive and negative designations have been our standard ever since. So he made that decision back in I guess the late 1700s sometime, when he wasn't writing the Declaration of Independence or going off to Paris for diplomacy. He was doing a lot of or writing down wise sayings. He was messing around with electricity. So he didn't know anything about electrons or protons, though. So if he had, he might have made the opposite choice, because electrical engineers, when they're designing electronics, the things that they have to manage, they got to corral things to make an electronic device work, is electrons. And electrons are negative. And it's a pain in the neck when you're working on like a circuit equation or a semiconductor equation, and you're working out all these cool concepts with the electric field and current and all that stuff, and you got to remember yourself, okay, now that's for a positive current, but what actually moves are the electrons. And you can make a note of this. In a regular circuit, man-made circuit, copper, whatever it's made of, it's the electrons that move. The protons don't really move. So an electrical engineer is trying to herd these little electrons around. They're negatives, and it makes his life a little more complicated than it would be if Ben Franklin had chosen the opposite way. If he had chosen the opposite way, which he could have, then electrons today would be rated positive charges, and a lot of math errors would be avoided by electrical engineers. But that's what we have. Now, a little bit after not Sir Benjamin Franklin, just regular Mr. Benjamin Franklin. A little bit after him came another guy over in England named Michael Faraday. And Michael Faraday is the fellow who discovered that an electric current can be generated by a magnet. If a magnet is moved through a loop of wire or a circuit of wire, it will induce electric current to flow. And that is how the big generators and little generators work. If you have a little Honda generator for your house, for in case of a hurricane, it will be running on the basis of magnets moving through a lot of coils, or moving next to a lot of copper coils of copper wire. And Faraday's the one that figured that out. He's kind of an interesting guy. He was born the son of a blacksmith, and very humble beginnings. And in England, in those days and in this day, their society has a very stratified class structure. So the upper class and the lower class, like the blacksmith and the blacksmith's family, which Michael Faraday hailed from, they would not really mix. They wouldn't have much to do with each other. And for Michael Faraday, he became extremely famous. The Queen of England honored him as one of the greatest scientists in the British Empire. And he really was actually one of the greatest scientists of all time, in my opinion. But he didn't know any calculus. He never went to university. You guys have more math than he did. And if you've had calculus, you've got a ton more math than Michael Faraday. And yet he discovered an enormous amount of electromagnetic and chemical effects. He wrote a huge amount, discovered a huge amount, and he taught a huge amount in London. They made a special lecture hall just for him, so that he could teach the general public all about electricity and magnetism and chemistry. A very famous guy, and very unusual that he would come up. Now, here in the United States, it's not like that. That's one thing I like about UCF. We have people, this is not a highfalutin place like Harvard or one of those Ivy League schools where it's mostly rich kids. But here, it's everybody. Everybody comes. and everybody works their you-know-what off, and that's what I like. I like working with those kids. And everybody keeps an eye out for spiders in the classroom and stuff. You know, you don't find that in the Ivy League. They just, la-di-da up there. And I taught up there, and so I know what it's like. And it's a significant difference, and I really love UCF for that reason, because you guys work so hard, which is the same way that Michael Faraday operated. Another famous guy came contemporaneous. He was young when Michael Faraday was getting older, James Clerk Maxwell. And what he figured out was how the magnetic field and the electric field that Faraday, connected. Faraday figured out that they were connected and they were dynamic. Electrodynamics is what he basically discovered. James Clerk Maxwell, he figured out all the math backbone of the electromagnetic field. So he was a guy from Scotland who did go to university and knew an enormous amount of math. And in fact, he could have taken over any math department in all of God's green earth if he had wanted to. But he was a physics specialist. And he did have something interesting to say about mathematics. And I want to read this quote to you. You can write down the first sentence if you like, and then look it up later. Mathematicians may flatter themselves that they possess new ideas, which mere human language is as yet unable to express. Fine. Let them make the effort to express these ideas in appropriate words, without the aid of symbols. And if they succeed, they will not only lay us laymen under a lasting obligation, i.e. gratitude, but we venture to say they will find themselves very much enlightened during the process, and will even be doubtful whether the ideas as expressed in symbols had ever quite found their way out of the equations and into their minds. Now what James Clerk Maxwell is saying in that is that the egghead mathematicians ought to do the same things that we do in this class. And that is, we try to think about the meaning of these concepts. And that's what you guys work really hard to get a hold of. And that's what James Clerk Maxwell is saying. That's fine, all these nice little equations. That's why I always tell you, the equations are nice, but they're there to serve us. We don't serve them. They're not our master. We should be the masters of them. And the way to do that is by, as Maxwell says, express these ideas in appropriate words. And that's why I work so hard with you about getting words down to give a concept to these equations. Because equations, anybody, they could train monkeys escape from the circus to do equations just about, or engineering majors, either one. But figuring out what those ideas mean in appropriate words, that's the tough part. Now, soon after Maxwell came J.J. Thompson. And in 1896, he made a very famous experiment with the mysterious cathode ray. A cathode and an anode are the fancy terms for the positive and negative pieces of metal in an electric circuit. In other words, take two pieces of metal, collect one end to the positive terminal of your battery, the other end to the negative terminal of your battery, and you have a cathode and an anode. And what they found is, if they have a big enough voltage, it'll generate these mysterious rays. And the rays, they knew that if you streamed the cathode ray at certain substances, that they would phosphoresce, they would emit light. And our television today is based, the old-fashioned TV, non-flat screen, is based on that phosphorescent effect of electrons hitting an atom or a molecule that will then phosphoresce and emit different colors of light. And that's what they did. So this device down here, this is kind of down here at the bottom right, that's a diagram of his device. I have a photo of it I'll show you in a second. He used parallel metal plates, one positive and one negative, to figure out if these cathode rays were positive or negative. And he said positive repels positive, positive attracts negatives. They knew that. And so he said, if I make one of my plates up here positive and one down here negative, and if I send my cathode ray between one of them, it's going to dip upward or it's going to dip downward. And if I can observe which way it dips, I'll be able to figure out if my cathode ray is a positive or a negative. And that's what he did. And what he was able to prove was that not only was it negative, it was actually a particle, the electron. J.J. Thompson is the one who discovered the electron in these experiments. He proved that it was a particle and that it had mass, and that the ratio of the electric charge to its mass was a very precise number that he was able to measure, the charge to mass ratio. So in his device, here's the cathode down here marked C, and that's where you generate the mysterious cathode rays. Then you send it through the gooseneck over here, and in the gooseneck you kind of narrow the beam down. You eliminate a lot of the side rays, and you just get the stuff in the middle of the beam. Okay, so you narrow down your beam, and then you send it through these plates, and you hope that the plates will deflect the ray upward or deflect the ray downward. And then you could measure the amount of deflection. Now, here's another view of it. This is kind of streamlined. You can make a sketch of this. Here's your cathode ray source over here on the left. And he sends it through the gooseneck, and then through the gooseneck it goes into this region between the two plates. So the upper plate is positive in this diagram. The lower plate is negative. So if those cathode rays are positive, they're going to dip downward, away from the positive plate toward the negative plate. Similarly, if the cathode rays are negative, they're going to dip upward towards the positive plate, because negatives like to go towards positive, electrically speaking. Opposites attract, likes repel. And this is what he found. Bam! He found that the cathode ray deflected upward, and that means that he has a negative particle. And he did a bunch of trig and a bunch of calculus and figured out the exact ratio of electric charge to mass. Not too hard to do, but we're not going to go into the details of that, but he was able to measure it based on where that little glass tube, the inside of the glass tube, the very end of the glass tube, was painted with phosphorescent paint. So when those cathode rays hit it, wherever they hit it, it glowed. And that's what he was able to observe. Now that same technology is what you see in these older TVs, the CRT display, they call it, the cathode ray tube. In the back of it, over here, in this end here, there's a cathode ray source, very highly controlled, very high voltage, and then there's a bunch of electromagnets, and the electromagnets go on and off at a certain rate, and they aim the electrons, the beams, here and there on the screen, and they light up different little pixels of color, and you see the light from each of those pixels as a football player or whatever you're watching on TV. A zombie in The Walking Dead. Michonne chopping the head off a zombie. She's my favorite in The Walking Dead. Anyways, that's how the old-time TV... I actually have one of these in my office. But most of you guys probably don't even know what these are, because you're all shrimpy little 20-year-olds and stuff, and you just have always had flat-screen TVs. Yeah, question?
How do you get the metal to be either positive or negative?
You hook it up to a battery or to a circuit, an AC circuit. He probably used a battery, big battery, So the top plate to the positive terminal of the battery, the bottom plate to the negative terminal of the battery. There you have it.
So it's not like when you set the car, it just charges it and maintains it because it's constantly...
Yeah, because there's no current. There's no current flowing from plate to plate. Okay, so it just charges the plate and it sets up an electric field between the two plates, and the electric field works on the cathode ray and deflects it upward. So it's kind of cool. Here's a picture, and here's the deduction that Thompson made. He said these cathode rays, I think that they're little tiny particles, and I think that they're part of an atom. Nobody had really figured out what atoms were, and they hadn't really proven that atoms existed. They thought that they existed. They had lots of evidence, but it was these experiments that really proved that what an atom is and what its structure is. And so he thought that these electrons were all kind of smushed together into a big blob of positively charged matter. Just like little nuggets of, little nuggets of Reese's or M&M's are embedded in a McFlurry at McDonald's. You know, they're all kind of mixed in there. So that's kind of what... I didn't bring any lunch today, so I'm making all these allusions to food. So I haven't eaten my lunch yet. I'm kind of hungry. Big disaster. Anyways, but now the thing is, he thought that this theory of the atom, it's called the plum pudding model, after something that they eat, some kind of plum pudding that they make over there in England. I've never seen it. But it was basically this, a big blob of positively charged matter with electrons sprinkled through it. But a guy that came after Thompson, named Rutherford, figured something else out. And he refined the model, and he was able to show that, no, it's not really the way you figured it there, Mr. J.J. Thompson. It's a little bit trickier than that. Now, there was another kind of mysterious ray that they had discovered, an alpha ray. And the X-ray are still known as X-rays, the unknown X. And the other thing that they had was an alpha ray, and gamma rays, the unknown gamma. Okay, so the alpha particle was one of those mysterious things. And what Rutherford said, he knew that the alpha particles were positive. You know, that you take a chunk of radium or something, and it puts out a lot of these alpha rays, and you focus them, and you make a nice narrow beam. We know they're positive. And what he did was he slammed them into a thin foil made of gold. And if you know anything about gold, you know that gold can be pounded really, really, really thin. So he took the thinnest film of gold that he could, and he said, I'm going to slam those alpha particles into the gold and see where the smithereens go. Right? Now, he didn't really see anything broken apart, but what he did find was that the alpha particles scattered. They went into the foil, and then they got deflected left and right, up and down, and even some of them deflected right over here. Look at this one. This is called backscattering. So here's his device. Over here is this source of alpha particles. And then he sends the beam in through this little opening, and this ring-shaped kind of cylinder with a little bit of a hole in it, that's his detector, zinc sulfur detector. It will glow when it gets hit by an alpha particle. All right? So in the middle of it, he puts his target, and he just slams those alphas in there, and then he counts how many alpha particles hit at this angle, how many at this angle, how many at this angle, and he just counts it up, all the different angles, and including these backscattering. And these were really important. So write down the word backscattering. Rutherford experiment, backscattering. Big, huge observation, because it can only happen if there's electrical repulsion. And electrical attraction cannot produce that. And what that told Professor Rutherford is that there were very small objects that were positive. And those positive objects are what we call nuclei, the nucleus of the atom. We would not have deduced that without observing backscattering of the alpha particles. So a backscatter is anything that deflects it more than 90 degrees. So if it comes in straight and it goes 90 degrees right, that's a 90-degree scattering event. If it goes in straight and scatters 90 degrees to the left, straight to the left, that's a 90-degree scattering event. But if you come in and hit the target, and not only do you turn left, but you keep going to like 110 degrees, so from straight ahead to 110 degrees, that's you're actually going back the way you came a little bit. That's backscattering, and it will not happen without a positive nucleus. So here's what they expected to find up here. Something, the alpha particles kind of zipping through there, and a positive blob with a bunch of little electrons in there, the plum pudding model. But what they found was that down here, that they were getting these backscatters. So this arrow right here is the key arrow to remember. That's a backscattering. Most of them went just right through. They didn't really interact with anything. So they knew that whatever they were interacting was pretty small. It was so small, most of their alphas missed. But they got backscattering, and they got some regular forward scattering as well. But the backscattering was the giveaway. We have got something small, something that repels. All right? In other words, we have a positive nucleus. So backscattering, positive nucleus, Ernest Rutherford. And what we know now is that atoms are made primarily of electrons, protons, and neutrons, except for the main form of hydrogen, which is just a proton and an electron. It doesn't have any neutrons in it. Everything else has neutrons in it, in the nucleus. We think that they're bundled up, positives and neutrons in the nucleus. So kind of draw a little blobby container, 2 protons, 2 neutrons, and if it's going to be a neutral atom, and nature likes to have neutral atoms, it'll have 2 electrons, and we think that the electrons are kind of zipping around like little planets. The Rutherford model of the atom was a nucleus and electrons zipping around on little tiny orbits like little planets orbiting the SUN. And this particular diagram is a diagram for helium. That is a helium-4 nucleus and 2 electrons making up a helium atom. This little rectangle is the upper rightmost rectangle of the periodic table, the helium rectangle. So it says the name, helium, the symbol, He. The 2 symbolizes the number of protons in the nucleus, 2 protons. The number 4.003 tells you the approximate mass of the atom itself in terms of atomic mass units, 4.003. So that means that you've got 4 things in the nucleus, and 2 of them are protons, so 2 of them are also neutrons. So 2 protons, 2 neutrons, and that's what we've got. And this is why we're heading for the periodic table. And we're going to try to understand as much as we can about electrons, protons, and especially molecules after we tackle the periodic table the next week or so. Okay, I have a question for you on your clicker, so fire it up again. let's get a mental IQ test. And you better hit the refresh key. Here's your question. And I'll give everybody a point for whatever you vote, but try to see what you think is the most reasonable and vote for that. If like charges repel, then what keeps a nucleus of protons and neutrons together? I mean, protons, they should, repel each other. But they're still bound. They're very tightly bound. Think. Read carefully and think. Fifteen seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Aha! Caught you. Here's the vote, and the correct answer is this. There's a third force. 27% of you voted for that. Now, neutrons neutralize the charge of a proton. That's gibberish. Actually, that's like something they say in a science fiction movie. We'll neutralize it with neutrons. We'll reverse the polarity. Protons, B, proton spin. 7% of you voted for that. 50% of you voted for neutralize, for A. For B, proton spin, 7%. Protons do have spin. It's called intrinsic angular momentum. That is correct. But a correct concept, but it's not the correct answer for this question. The correct answer is that there's a third force. And students, go ahead and make a note of it. This force is called the strong nuclear force. Of the four forces of nature, this is the strongest. Stronger than electromagnetic, way stronger than gravitational. And there's a second nuclear force called the weak nuclear force, which is related to electromagnetism. D, option D, gravitation holds them together. No way, Jose. Now, I'm not penal. Who voted for E? I don't know. E's not even an option here. D is incorrect, and make a note next to option D in your notes. Example 7.1 in the textbook in chapter 7 is about the comparison between the gravitational interaction of an electron and a proton and the electromagnetic interaction. And what you'll find when you calculate that, or when you work through that example, is that the gravitational interaction is much weaker. So much weaker, you don't even need to worry about it ever, if you're thinking about individual atoms. Now, planets and stuff, planets are so big that, yeah, you have to handle gravity with planets and stars and stuff, but not with atoms. Okay, let's talk about the Coulomb interaction. And we'll start by talking about Coulomb himself. He was a military engineer down in Martinique in the Caribbean. And in the year of independence, 1776, he moved to Paris right into the middle of the French Revolution, but he became an academic scientist there and very successful. He developed a balance, not for measuring masses, but for measuring electromagnetic forces. A regular balance where it tips up and down, left and right, that measures gravitational forces, relative weights of two objects. What he developed was a small horizontal balance that would, instead of dipping up on the left, down on the right, or up on the right and down on the left, he found that you could build one that twisted horizontally, in which the twist angle correlated to the force if you had your objects arranged not vertically but horizontally from each other. And I'll give you a diagram of it in a second. It's called a torsion balance. So make a note of that, torsion balance. And he used that to figure out the force, the law of electromagnetic interaction, which we now call the Coulomb interaction, after Professor Coulomb. The torsion balance works kind of sideways. Now, here's a perspective view of the torsion balance. There's a fiber running vertically here. This is the fiber that gets twisted. This horizontal kind of orangey line here represents a very light rod, so maybe aluminum or something. And at the end is a small weight equal to this one on this end that gets charged electrically. So, in other words, a little bit of tribal electricity. So that might be made of rubber, and he charges it up with silk or something like that from the triboelectric series. And then these two black objects are fixed in place. All right, so the torsion fiber, what you do is you measure how many degrees of twist is created when you charge up the two black bowling balls and the two little red ping pong balls. Okay? And that'll cause the system to twist in this plane. So it'll be like this. It'll move like this. Okay, you see what my arm is doing? This is how the torsion balance moves. All right, it'll move like this. And the amount of twist is measurable with that fiber. And so many newtons per degree of twist. All right, here's an overhead view. Okay, so here's the rod. And right in the middle here is the torsion fiber. Okay, so we're looking down from above. And at each end here is this little red ping pong ball shaped thing that's going to get some triboelectricity. And then here are your two bowling balls, and they're going to get charged up as well, but they're fixed in place. The thing that moves is the two light ones, the two red ones. Okay, so we charge them up. We charge up the black ones with as precisely as we can, and then we measure the force. What happens? Well, if they're attractive, they'll move toward each other like this. So this 2-inch diameter object goes a little bit closer, and it produces a little bit of twist. And so does this other one on the other side. And that degree of twist is what allows you to figure out how many newtons of force are being applied by the electromagnetic interaction. It's a force that arises because of charge. Okay? And here's the distance that you use to calculate the distance dependence. So you go from the center of this red one to the center of the bowling ball. That's distance r. If they're charged precisely, you can then figure out the law of electromagnetic interaction. So you measure the distance r and then correlate to the twist angle. The twist angle gives you the number of newtons. And then you can figure out your force. Here it is. The Coulomb interaction is very similar to universal gravitation. First of all, it goes in a pairwise interaction. So charge to charge in this case. It's not mass to mass, The symbol we use for a charge is little q. Sometimes capital Q, but usually little q. All right? So Q1 and Q2, and the distance between them is also the other physical factor. So how big your charge is, Q1, Andrew, and Q2, the distance apart, and what Coulomb found was that the further apart they were, the weaker the force. And this is the force law that he figured out. He made a lot of experiments, a lot of measurements, and this is what his conclusion was. That the electromagnetic force was equal to the product of Q1 and Q2 in the numerator, the two charges, the load of charge on the bowling ball, the load of charge on the red ping pong ball, divided by the square of their separation distance, r. And then he has just like the constant g in universal gravitation, he has another constant, a conversion constant called the Coulomb constant now, symbolized K, and that is this item right here. So this should look a lot like gravitation to you, okay? Because gravitation is g times m1 times m2 divided by r squared. This one, K, a constant, times Q1 times Q2 divided by r squared. And that gives you the magnitude. There are some features of this that are not the same. Okay, first of all, unlike gravitation, there are two kinds of electric charge. Charge is not measured in kilograms. The metric unit, which we'll talk about on Thursday, is the Coulomb, not kilograms. Two charges can repel if they're the same kind, if they're like charges. So positive repels positive, negative repels negative. Gravitation is never like that. But here's an important thing that is the same between the two, and that is they're both inverse r squared forces. These are the two in nature, the two inverse r squared forces that we know of in nature. These are the only two. The calculus behind this statement is really intense, but the meaning of the calculus is that this force has infinite range. Gravitation also has infinite range. It also means that the mass of the photon is exactly zero, which is kind of interesting because the photon interacts with a gravitational field even though it doesn't have mass. Now, I'm going to skip through this. I'll skip through this slide here, the electroscope. I'm going to talk to you about some other stuff here. Let's talk about this diagram. We'll talk about electroscope next time. And have your clicker ready. We got another clicker question. Go ahead and sketch this array. There's two charges on top, two in the middle, and two on the bottom. I always make my electrons blue and my protons red. The proton charge is symbolized E. The electron charge is symbolized minus E or minus 1E. So this array of charges is two electrons on top. The middle set is a proton and an electron. And then the bottom set is two protons. All right? Now, I have two more clicker questions for you. Same array. Here it is. Which pair has or have repulsive interaction? So think carefully about this. $20 seconds to answer. 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys voted for. Yay! Most of you got it right. Bottom and top, because they're both like charges top and like charges bottom. All right, next question. This one's going to burn your brains majorly. For this array, this linear charge array, an electron and then 2 protons, what is the direction of the net force, the net electrical force, on this rightmost proton? Is it leftward, is it rightward, or is it 42? No? It's not C. $20 seconds. $10. Good, Corey. I like seeing that, you know, going. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Wow. You guys are geniuses. Your homework assignment tonight, I'll ask you a question why that is the case. You're dismissed. Look for homework by supper time tonight. Due on Thursday.